In this video, we're going to go a little deeper into hydrolysis. And we're going to compare the hydrolysis of salts of two different weak acids. We're going to look at how a metal ion, cation, reacts with water. And then we're going to look at a case where maybe an ion can become acidic or basic, and how do we know the difference? So first, we're going to compare the hydrolysis of acetic acid to formic acid, which we've already looked at. So here is acetic, the salt of acetic acid, so something like sodium acetate or potassium acetate, when put in water, is going to produce some hydroxide ions, not many, but some, plus some of the acetic acid. It will reach equilibrium. We learned previously that the hydrolysis is going to equal Kw over Ka. We also learned in a previous experiment that Kw is 10 to the minus 14. The Ka of acetic acid is 1.8 times 10 to the minus 5th. So the K value for this reaction of acetate ions with water comes out to be 5.6 times 10 to the minus 10th. Again, a rather small number. But what we need to look at is the 10 to the minus 10 and compare that with the 10 to the minus 11. So the formate ion has a lower 10 to the minus 11, a lower hydrolysis constant. So let's talk about the acetate. Acetate has a larger hydrolysis constant, which means more hydrolysis. More hydrolysis means more hydroxide. Since that's what's produced in both of these reactions, hydroxide. So, more basic. And higher pH. So smaller hydrolysis constant means less hydroxide, means the solution will be closer to neutral, to pH 7. Okay, so we need to learn how to interpret these numbers. What does those constants actually mean? All right, now some metals, the ion, not just the metal, but the ion reacts with water. We showed you in Chem 110, for example, that when a metal ion is hydrated, it's dissolved, it is surrounded by 6 water molecules. So when zinc ions are placed into water, this is what's formed. It's called a complex ion. It's not just zinc ions by itself. It's zinc surrounded by 6 water molecules. So what we end up with is something like this, ZnH2O6. It's a big complex, and it's charged. The charge is actually spread out. However, another water molecule can come in here and snatch one of these hydrogens. And you guessed it, an equilibrium. So now the zinc has 5 water molecules attached to it and a hydroxide attached to it, and its charge is now +1. The water molecule that we have here grabs one of the hydrogens, and we get a hydronium. Again, this doesn't happen a lot. It has a small Ka. Nevertheless, solutions of transition metals tend to be acidic because they react with water to form hydronium. Now, what about an ion like sodium? Well, sodium plus water gives us no reaction. That's because we're not going to produce sodium hydroxide. It's just not going to form. It's a strong base. So we're not going to form a strong base. So group 1 metals do not react with water. Transition metals tend to react with water. So this is the equation for any transition metal. The only thing that would be different would be the metal and the charge. But if you used iron or aluminum or silver, the charge would be different. Of course, the metal would be different, but it's the same reaction. It's 6 water molecules. You just substitute the metal ion and the charge, of course. Lastly, I would like to look at a situation perhaps where we put sodium bisulfite into water. Okay, so what will happen if I put this ion into water? Well, let me give you 2 possibilities. The hydrogen could go with the water and produce hydronium plus sulfite ions. That's one possibility. But couldn't this also happen, where the bisulfite ion reacts with water and actually takes a hydrogen from the water, and we end up with hydroxide plus H2SO3? Well, which is it? Is it the top reaction or is it the bottom reaction? Here's how we know. We must compare the equilibrium constants. You must compare the equilibrium constant for this first reaction with the second one. Larger equilibrium constant tells you which reaction will occur. All right, so if we look at this first reaction right here, we need to think a little bit about Ka. There's 2 hydrogens with H2SO3. There's 2 hydrogens here. That means there's 2 Ka values. There's a Ka1 and a Ka2. Ka1 is the first hydrogen reacting. Again, we're talking about Ka for the moment, not hydrolysis yet. In this reaction, we get hydronium plus bisulfite. In the second reaction, we start with bisulfite. And this too means the second hydrogen is going to come off. And we get H3O again, but this time we get the sulfite ion, which is a -2. Okay, now if you look it up in the textbook, in the appendix, this is Ka1, and you need to distinguish when do I use Ka1 and when do I use Ka2, and that's a big challenge for most students. So I just looked these values up in the textbook. You should understand that Ka2 will always be smaller than Ka1. Always be smaller than Ka1. Okay, so let's take a look, and we want to compare the K values for these 2 reactions. Okay, so the K for this first reaction is going to equal Ka2. That's this reaction that we just did. They're identical if you compare them. So that is going to be Ka2, which equals 6.4 times 10 to the minus 8th. Okay, so now we have the first K value. Let's move this up. And let's now determine the K value for the second equation. Well, K is not Ka because we produced hydroxide. So, how do we find this? Well, the K value for this second reaction is going to equal, like our hydrolysis, Kw over one of the Kas. We've seen that time and time again. But is it Ka1 or is it Ka2? Which one is it? Well, let's take a look. You will notice right here that we have a -2 charge. That's the largest charge in that equation. We used 2. So those match. The charge matches with the Ka. In this case, the largest negative charge is -1. And you can see that we've produced H2SO3. H2SO3 only shows up in the Ka1 equation. So this is going to be Kw over Ka1. So 10 to the minus 14. Here's our Ka1. We just looked that up in the textbook. That's 1.6 times 10 to the minus 2. All right, again, we're going to compare the two K values. This comes out to be 6.3 times 10 to the minus 13. Okay, so you can see that this K value is larger. So Ka2 is much bigger than the Kb, which is also the Kh, which we came up with right here. In other words, 6.4 times 10 to the minus 8 is much greater than 6.3 times 10 to the minus 13. So in this reaction, which has a bigger K value, for that equation, so it wins, so to speak. So more hydronium is produced than hydroxide, so it will be acidic. So that's how you tell if something like sodium bisulfite is acidic or basic. You have to look at both possibilities, both equations, determine the K values for both of them, and then see which one's larger. The larger one will tell you if it's going to be acidic or if it's going to be basic.